Okay, so welcome to lecture number 5. Now let's go back to first lecture number 4. We were working on reciprocal lattice. I'll repeat what we said yesterday one more time in the beginning. So today's topics are, first thing we will cover is continue on this reciprocal lattice business and finish it off. I'll show you reciprocal lattices for simple cubic, body centered cubic and face centered cubic. Following that, I am going to then come to the main thing for which I was making this reciprocal lattice, which is I will show you the Brillouin zones, or a first Brillouin zone at least I will show you. This Brillouin zone construction is something very similar. I mentioned that in while doing crystal structures or crystal lattices, I mentioned that this Wigner seed cell, though not used often in direct lattices, but it has a great utility in reciprocal lattices, and that is really what that construction will be in Brillouin zone. So, that we will do today. And then why are we doing Brillouin zone? Something very interesting will happen on the zone boundaries. On the zone boundary, the boundary of Brillouin zone, something will happen, and that is related to electron diffraction, and therefore any electron wave or which conducts, because of which conduction happens, therefore something will happen to that. So, those are the three topics which we will cover today. So, let us recall what we did in lecture number 4. We said that if A1, A2 and A3 are, if A1 I then is 1, 2, 3, that means if I have 3 primitive lattice vectors A1, A2 and A3, then any lattice point in the lattice, direct lattice, can be generated by this vector R, which can be reached by using integer values of n1, n2 and n3 multiplied by this lattice, primitive lattice vectors. So, we can locate any lattice point on any with this vector R. So, R represents the lattice points. If that is so, then we defined another vector this way. Initially, we just defined it, that consider there is a vector like this. Then we decided that we will call B1, define B1 like this, B2 like this, expression here, B3 like this here, and where Vp was the volume of the primitive cell in direct lattice, the real lattice, where the lattice points are arranged. So, those in that lattice, and I will use that word direct lattice for it as opposed to reciprocal lattice. So, that is the volume. So, that volume can, if I have three vectors A1, A2, A3 defining the primitive cell, then the volume of that primitive cell can simply be taken as the scalar product, here. So, that is the volume of the primitive cell. Now, we said that the way I have chosen this k is that I want that e to power j capital K dot R should become equal to 1, and you can notice that if you substitute this k and R, then what will you get? If you substitute in there k and R, you can prove that this indeed is equal to 1 for these particular values of k. So, these values of k when substituted in will give you this 1, and this is what we had done. And I mentioned that this then gives you in reciprocal space, this allows you Fourier, you can do a Fourier analysis of any electron wave, and if there is a periodicity in direct lattice, then these are good functions for Fourier analysis, but that is not what we really want to do. What we want to do is this. So, if A1, A2, A3 are the 3 primitive vectors which define a unit cell, a primitive unit cell meaning one lattice point per cell, then if this is really what is defining the primitive cell in the direct lattice, then if I generate B1, B2, B3 like this, then similarly I can think of B1, B2, B3 also as 3 vectors which define a unit cell, but now this time in reciprocal space. What is the meaning of reciprocal space? Reciprocal space simply means a space where dimensions are inverse of length, which you can see that this has a dimension L square, and then Vp of course is volume. So, L cube. So, then L square divided by L cube gives you 1 by L. So, B has dimension of per unit length, all B's have dimension of per unit length. So, therefore, this space we are calling as space is reciprocal space. That is the reason we started calling it reciprocal space. But if B1, just like A1, A2, A3 3 vectors defined a volume, and a volume which could be repeated and generated, and that generated the lattice points. Similarly, we can think of B1, B2, B3 generating a volume which then can be repeated and it can generate a lattice, and that we will call as reciprocal lattice, which obviously belongs to reciprocal space. So, that was the general idea. So, once I have defined that, so now what I am going to do is I am going to apply this to various conditions of simple cubic, body centered cubic and face centered cubic. So, let us begin with that. Let us start with therefore, simple cubic system. Just to understand this, what are the lattice vectors? So, primitive as you know that simple cubic is simply like this, with lattice points being here, 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 at the corners of the unit cell are the lattice points. And if the lattice parameter is a, this distance is in the cube is a, then it is simple enough to write these lattice vectors, primitive lattice vectors, as being equal to a times x hat, a2 equal to a times y hat, unit vector in y direction, a3 as a times z hat, where you can think of, if you wish, this is x, this is y, and this is z, if you wish. So, these are the, and of course, it is the primitive cell. There is only one lattice point per unit cell, because lattice positions are only at the corners of the unit cell. All right. So, that is a simple cubic. So, corresponding to that, if we apply our formula for generating B1, so now our question is, what is B1, B2 and B3? So, that really is the question we are trying to ask, what are these values? But then you already know the formulas. Right here are the formulas. So, you can, given a vectors, you can figure out this, given Vp with using these formulas, you can figure out what B1, B2, B3 is. Now, what is Vp? Of course, in this case, that simply will be so simply there will be a cube times x hat dot y hat cross, which of course is just a cube. So, which we expected, that will be the volume of primitive cell, which will be just a cube. Let us use the black pen. Okay. So, now we can determine B1. So, if you determine B1, then B1 is what? Let us see, 2 pi by Vp, 2 pi by Vp, A2 cross A3. So, let us use that, 2 pi by Vp, Vp is a cube, A2 cross A3, A2 cross A3 is a y hat cross a z hat. So, what does that mean? That of course means 2 pi by a x hat, that is all that means. So, B1 is just this quantity. All right. Similarly, you can generate B2, B2 will be 2 pi by a cube y hat, and B3 will be equal to 2 pi by, so I am making a mistake here. So, I will fix this. So, this will be, since this is a squares, I should have yeah, that is fine, this is a cube, this should be only a, this should be only a. So, that is right. Now, 2 pi by a z hat, and clearly it is dimension of inverse of length. So, now notice, now make a comparison. A1 was a x hat, and what is B1? B1 is 2 pi by a x hat. What was A2? A2 was a y hat, and what is B2? B2 is 2 pi by a y hat, and we similarly look at A3, that was a by z hat, a multiplied by z hat, and B3 is equal to 2 pi by a z hat. So, now you can see by analogy what kind of lattice it represents in reciprocal space. Look, A1, A2, A3, just like A1, A2, A3, B1, B2, B3 are 3 vectors, and they have same form, as A1, A2, A3, except instead of a, now in the front we have 2 pi by a. We have 2 pi by a instead of a. What does that mean? That means I can draw therefore a reciprocal, in reciprocal space also I generate a lattice which looks like a cube, but this time in reciprocal space, and that will be simple cube. So, in reciprocal space, lattice point will also be in, just like by analogy, that this must also be therefore simple cubic. So, at the corners only, and the length of this now should be 2 pi by a. So, lattice parameter in reciprocal space, in reciprocal space. So, the statement I make is that a simple cubic lattice of lattice parameter meter A transforms to a simple cubic lattice of lattice parameter two pi by A in reciprocal space. So, that is what it is, that a simple cubic leads to a lattice in reciprocal space, which is also a simple cubic, and the lattice parameter of course is 2 pi by A. So, that is the transformation. So, that is what in other words I can generate another lattice in reciprocal space, which looks like by just repeating this volume, this unit cell I can keep repeating it, and then I will generate a. So, I will generate various lattice points, and those lattice points will be defined by this vector k. If R defines the lattice points in direct lattice, then K defines the capital K defines the lattice points in reciprocal lattice. All right. So, with this, let us do this, let us move on. Now, we will move on to body centered cubic. Now, this body centered cubic we are going to do now, and since in yesterday when I was doing last lecture, when I was doing direct lattice in body centered cubic, the primitive vectors was not looking very nice. So, I am going to draw that again. So, let us first write down our primitive vectors in direct lattice, which is A1. We had taken this as A by 2 y hat plus z hat minus x hat, and A2 was equal to A by 2 z hat plus x hat minus y hat, and A3 was A by 2 x hat plus y hat minus z hat. So, let us draw these lattice vectors. First, let us draw these lattice vectors. So, you know what I am showing you here in this case is, so what I have done is shown you I have shown you a cube, which I am going to show a body centered cube. So, you know that the lattice points are located. In fact, let me put crosses in there to show you the lattice points. With the blue I will put crosses like this, 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 and like this. These are body centered lattice points. As you know, these are the places where these are body centered lattice points. Now, let us do this. In order to draw this primitive lattice vectors, what we are going to do is let us take the center at the let us take the origin right at the center, right here, and at this point use this lattice points as the origin, and with respect to this origin, let us draw all these lattice vectors, so that all these lattice vectors remain within the cube itself. And the orientation of course, I am using is x in this direction x, in this direction y, and in this direction z is what I am using. So, let us look at A1. This A1 we are going to move A by 2 distance in y direction, A by 2 distance in z direction, and A by 2 distance in the minus x direction. So, let us do that. So, from this point let us move on to in y direction, let us move to A by 2, in z direction let us move to A by 2, and then in x direction let us move to A by 2. So, I will generate this lattice point. Here is the lattice point right here. So, let us generate that. So, right here is the lattice vector. So, I am going to draw this from here to here, and this is A1. This is A1 lattice vector. And similarly, let us do A2. A2 we move half in z direction right here. So, we move up to z direction and half, and then we move in x direction half, and then we move in minus y direction right here, and we move and then locate this A2 point. So, this must be the A2 vector. This must be the A2 vector. Similarly, A3 vector x direction, let us move half. So, in this plane we move half, in y direction we move half, and in z direction we move half right here, and then this is therefore the A3 vector right here. So, this is the A3 vector. Using these three vectors, you can imagine, you can construct a volume and you can construct a primitive cell. And now, in this primitive cell, clearly if I take the volume of the primitive cell, then you can carry out this exercise A1 dot A2 cross A3, you can calculate this, and this clearly will come out as, you try this out, this will come out as A cube by 2. And that should be obvious, because if this lattice parameter was A of the body centered cube, then whole volume should have been A cube, and since there are two lattice points in such a, in this whole picture which I have drawn with black lines, there are two lattice points. So, if you draw a primitive cell which has only one lattice point per unit cell, then the volume of that primitive cell should be half of the whole cell. So, that is A cube by 2 therefore. So, that is the primitive cell. With this, now let me write the B1, B2 and B3. So, B1, B2 and B3 are the three things we want to write down again. So, again you use our same formula, 2 pi by Vp A2 cross A3. So, we do this 2 pi by Vp A2 cross A3. So, you go ahead, do this calculation, and we will find that B1 will come out as 2 pi by A and B2 will come out as 2 pi by A, and B3 will come out as 2 pi by A, or Z plus x actually I should write. In fact, I should let me write down as Z plus x. B3 as this vector. Does this look familiar to you? Does it not look like FCC? So, let us do the recall here. Let us make a block here. Recall for FCC, not BCC. For FCC, face centered cubic, we had A1 primitive unit vectors as A1 A by 2 y plus z, A2 we had as A by 2 z plus x, and we had A3 as A by 2 x plus y. These were the primitive vectors for face centered cubic. Now, compare B1, B2, B3, do not they look the same, except that remember here I have A by 2 in front, and here I have 2 pi by A. So, if I write this quantity as something as 4 pi by A divided by 2 y plus z, then you can think that, so clearly then a body centered cubic, these vectors therefore, this A1, A2, A3 body centered cubic, when we look at the reciprocal vectors, then reciprocal vectors have a form of face centered cubic. That means, in reciprocal space, the reciprocal lattice of a BCC is FCC. Of body centered cubic is face centered cubic of lattice parameter 4 pi by A. By comparing this form, that I have a 4 pi by A here and I have a here, just a here on here, I have A's in here. So, therefore, I am comparing these A's and 4 pi by A. If in FCC the lattice parameter is A, then here in this case, then here in this case, then the lattice parameter will be 4 pi by A, which I have written here. So, that is what this will look like. So, if I transform this and I make FCC, then let me draw it, then it should be this primitive cell, these vectors should generate an FCC, something like this on the corners, then on the face center, here in the top, on the bottom, on the back side, on the front, on the left side, on the right side. So, these should be the lattice points. All these lattice points should get generated by these lattice vectors. So, in other words, BCC will look like FCC in reciprocal space. Very good. So, primitive cell will look of course different. Now, this picture I will show you. So, this is what I am introducing Brillouin zone now. Before I say, I will do this Brillouin zone one more time, but just, or instead I should say at this point of time, Wigner So, if we do a construction just like Wigner seed cell, which we did for direct lattice, then if I do that, then obviously whatever we did for FCC, if you go back and look at your Wigner seed cell for FCC, since in reciprocal space BCC looks like FCC, therefore, if I make a Wigner seed cell in in the reciprocal space, then it will look like a FCC, and that is exactly that same cell which I have drawn here in this page. We have this cell which has been drawn. I will come back to this page and note construction has already been shown to you that take any lattice point, draw lattice vectors, take any lattice point, draw vectors to all possible infinite number of vectors to all infinite number of lattice points which are there. So, you keep drawing them. For every vector, draw a perpendicular bisector plane, At the end of it, imagine you have drawn these infinite number of planes, because the infinite number of vectors, and you have drawn perpendicular bisectors to them. If you have drawn those, then after that, at the end of the day, there will be some volume enclosed, the smallest volume which will be enclosed inside. That volume which is enclosed inside, smallest volume that will be there will be enclosed by some planes, some portions of those planes. That was the Wigner seed cell in direct lattice. Same construction here. Now, this in reciprocal lattice is called Brillouin zone. This is called Brillouin zone, which I will talk about, and in 2 dimensional I will show you the construction eventually in a little bit. So, until then just hang on, and more importantly, well, not more importantly, but equally importantly, well, maybe I should make a little change. I should write this as small k. I hope you are comfortable with this drawing. So, in the sense that, remember, I am using k x, k y and k z here. What does that mean? That means that just like I was drawing these cells as, remember, A1, let us do an example here that will make your life a little bit easier maybe to understand. So, if we look at this page, let us just do A1, and BCC was this quantity right here. So, we will rewrite this A1 as equal to A by 2 y plus z minus x hat, and we will write B1 also, which was FCC like, which is right here y plus z. So, A by 2 y hat plus z hat. So, what was this A1 and A2 and A3? So, remember what we are saying is that if you have a direct lattice somewhere like this, and in that there is a x, y and z, similarly I should have something in the reciprocal lattice for corresponding to this. If I had, this is the orientation, then for this I should also have another, I should have orientation. That orientation we are now labeling as kx unit vector. So, this is kx direction, ky direction and kz direction, only to show that this is 3 orthogonal directions and in reciprocal space, that is, it is in k directions. So, in effect I could have replaced this quantity by k y hat, and I could have replaced this by k z hat. I could have replaced this by k y hat and k z hat, because they are just unit vectors in that space. I have used both x, y and z for both in the direct lattice also, unit vectors in direct lattice also here, and I have used it x, y, z also as unit vectors in reciprocal space. But if you want to be very precise and consistent with this diagram here, then you can replace in the reciprocal lattice these as kx, ky and kz unit vectors, because that is in reciprocal direction. So, that is all that means, and notice there are many g, f, h, p, d, n are shown. This is relevant. This picture I will take later when I actually draw the band diagrams for you, E versus K diagrams. I am going to use these to generate those diagrams. So, that will be the relevance there. So, at this point in time, just take a look at this picture from the point of view of the shape, and that shape, remember, is exactly like Wigner's heat cell in FCC. Since in reciprocal lattice was FCC of BCC, therefore, this is the Wigner's heat cell in the reciprocal lattice, whose name is of course Brillouin zone. Okay. So, with that, let us move on. Let us move on to also this. Now we will take FCC case. So, we have done simple cubic. Now, let us do face centered cubic. So, if we do face centered cubic, then recall again, I am going to repeat what we wrote in the last page. A1 of course was equal to a by 2 y plus z, a2 was equal to a by 2 z plus x, and a3 was equal to a by 2 x plus y. So, therefore, what was the volume? Volume of this primitive cell, this is the primitive vectors. What will be the volume of the primitive sector? Dot a2 cross a3, that is what you need to calculate, and that quantity of course will be equal to, go ahead and check this, a cube by 4, which I can write without really calculating it, because we know in FCC, if you take conventional cell of a cubic cell of lattice parameter A, so therefore, the volume will be a by cube, a will be a cube, and since that has 4 lattice, FCC has 4 lattice points per unit cell, whereas these vectors which I have written here a1 into a3 are primitive vectors. That means, the cell which will be constructed by this will have only 1 lattice point, therefore, its volume must be at least 1/4 of the conventional cell. So, I have just written it because of that reason. You can verify by doing actually these calculations. So, again, with this you will find that if we do the same thing, then we find B1 as equal to, in this case, 2 pi by a y plus z minus x, which I will also write as 4 pi by a divided by 2 y plus z minus x, and you will now clearly see why I am doing this, since we already discussed this. So, I am going to write this again as 4 pi by a by 2, this as equal to z plus x minus y, and B3. This I am presuming you can now do very easily, because formulas are there, all it is matter of taking cross products, nothing else. X plus y minus z. Now, what does that look like? So, this, of course, these lattice vectors give you FCC. They give you FCC. On this side face, right face, back face, front face, top face, bottom face. So, these are the lattice points in FCC. What will be generated by this particular primitive cell? Of course, primitive cell will be different, will look different, and that shape I have shown you earlier in the previous lecture. That primitive cell, I have shown primitive vector, and I have shown you the volume that primitive vector encloses, that I have shown you. But now notice, when you use these primitive FCC as these primitive vectors, and we do the reciprocal lattice transformation, then we get B1, B2, 3 vectors. Now, B1, B2, B3 vectors are, now look at the form. This form is much the same as BCC, which we did right here. Notice, for body centered cubic, these vectors look at a by 2 y plus z minus x, y plus z minus x, and now note is here, same thing, y plus z minus x, and now, but it is 4 pi by a by 2, now, rather than a by 2 in BCC, now in reciprocal lattice it is 4 pi by a. What does that mean? That means I am generating reciprocal lattice is BCC with lattice parameter with lattice parameter 4 pi by a. So, that lattice parameter is 4 pi by a now. All right. So, that is how easy it is. So, simple cubic transformed into simple cubic, body centered cubic transformed into a FCC reciprocal lattice, a FCC lattice transformed into BCC reciprocal lattice. You are welcome to try this for hexagonal lattices also, or any other kind of lattices. You will find hexagonal transforms into hexagonal itself, but that exercise, now I think you get the idea how this reciprocal lattice transformation is done. Okay. So, once this transformation is done, so let me show you the Brillouin zone or the Wigner seed cell. Wigner seed cell, again I will write that Wigner for FCC in reciprocal lattice. So, now since in reciprocal lattice the thing look like BCC, since it looks like BCC, therefore, let me first make this again correct, Kx, Ky, now you get the idea, small k is what I should write, not capital K, just to show the directions. So, now I have 3 directions Ky, Kz, and in this case you can see that since it is transformed to BCC, so Wigner seed cell, remember, looked like this for BCC. The construction again is same, take BCC reciprocal lattice, take one point, lattice point, draw vectors to all the infinite number of lattice points, draw a vector from this point you have chosen. From this point you have chosen, you draw lattice vectors, and that point chosen is right here. From this point, draw lattice vectors to all lattice points, then draw perpendicular bisector planes to it, and then the smallest volume that will form in this will have this shape, and obviously the lattice point will only be in the center then, and no other lattice point will exist, and that is a Wigner seed cell like construction, and this in reciprocal space is called in Brillouin zone again. So, this is the Brillouin zone of a FCC lattice. If you have FCC lattice and real lattice, for then it is a BCC in reciprocal lattice, and that is the Brillouin zone therefore. And in this zone again I have shown you these different k point, k, l, u, this sigma, gamma, delta, all these symbols are there. These again are going to get used later, not now, later they are going to be used in band diagram. So, be prepared to look at this picture again and again. All right. So, with this I will close the chapter on reciprocal lattice, and I will go on to now next topic, which is which was the Brillouin zone. I have already mentioned what Brillouin zone is, but what I am going to do now is show you the, I am going to work with you, and instead of in 3 dimension I will do this in 2 dimension to show you how Brillouin zone is constructed and what does it mean. So, let us do that part first. So, Brillouin zone, remember. Okay, so let us start with these Brillouin zones, BRILLOUIN. I have, as I have gone along, then I have already defined it, defined what it is, a Wigner cell in reciprocal lattice. Only thing I want to say right now is why do we bother about it? This plays an important role. What I am going to show you is, now since 3 dimension construction for FCC, BCC, you have to sort of imagine, and I have already given it to you. So, you can sort of imagine, and I have already told you how this construction is done. But if you have not really followed it, then of course, it is very difficult to do that in 3 dimension in by writing by hand. So, what I am going to do is I am going to do this construction for you in 2 dimension. I will do the same construction to make a Brillouin zone in 2 dimension, and then hopefully you will understand how this Brillouin zone in 3 dimensions were constructed, and then I will move on to show you the importance of it. First thing which I will show you is that something happens at the Brillouin zone, at the zone boundary. At the zone boundary, I will show you that the Bragg's diffraction condition gets satisfied, and therefore, electron wave is strongly reflected at these zone boundaries. So, that is really the purpose. Therefore, it becomes a lot more easy to analyze things in the reciprocal space, and this is where the importance of this comes in. And also therefore, this in this zone, you have to plot this EK diagrams. Of course, we will be using for that purpose, but eventually when we move on and we include the potential in our from free electron theory, if we start including potential, you will see that there is a band gap originating like in semiconductors, and it happens because of these reflections which are happening at electron reflection happening at Brillouin zones, Brillouin zone boundaries. So, essentially construct is from a lattice point draw a vector to all other lattice points. By the way, all this in reciprocal. All this in reciprocal lattice. So, from a lattice point, draw a vector to all other lattice points, infinite number of vectors like this. Then draw perpendicular bisector planes these vectors, again infinite number because infinite vectors are there. The smallest volume enclosed is the first which I will from now on abbreviate as BZ. That is the Brillouin zone, and I am now introduce the term first Brillouin zone. I might say Brillouin zone, I will mean that means first Brillouin zone, which means there are second Brillouin zone, third Brillouin zone, fourth Brillouin zone, etc., which you can see that the smallest volume was first Brillouin zone. So, now if you take the next largest volume which is enclosed by these planes, out of which you remove all the portion of first Brillouin zone, then whatever is remaining is called second Brillouin zone, and so on. You can keep developing this idea, but what we will be interested in is only the first Brillouin zone. So, that is the general construction. So, let me show you this construction. So, now what I am going to do is, now what I am showing you here is an array of point. Now, if you look at this point, then you can clearly see it is a point lattice. Take any point and the environment around it and look in any direction, the environment is same. Now, it is 2 dimension. So, I am going to draw now from these lattice points, I am going to draw vectors, and then I am going to draw perpendicular bisectors. So, perpendicular bisectors to these vectors in 3 dimension would have been planes, but perpendicular bisectors to any vector in this diagram will be a line. So, that is why it will become easier for me to draw. So, first of all, let us draw the lattice vectors, primitive lattice vectors. So, what is the unit cell in this for this point lattice in reciprocal space? So, here is my B1, let us say. So, this is, so here is B1 vector, let us say, this is the B1 vector, and let us say this is the B2 vector. These are the 2 lattice vectors which we have, which therefore, there are 2 vectors only, this is a plane. So, therefore, they enclose an area, that area is this, they form an area. So, this becomes our unit cell by defining this B1 and B2. Remember, no unique choice of B1 and B2, you can use many. This is in reciprocal space, and repeating unit of this cell, this unit cell, then would generate all the lattice points. So that is what this is. So now let us generate a Brillouin zone. So let us use this as a center. So let us say this is the center. Now let us draw the vectors. So if I draw a vector, then all the neighboring vectors first I will draw. So one vector is right here, 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 one vector right here, etc. So now if I draw perpendicular lines to it, then I will draw some perpendicular lines. So here is the perpendicular bisector which I will draw, or maybe I will use a different color for perpendicular bisectors. So here is a perpendicular bisector for this particular vector. For this particular vector, there is a perpendicular bisector going somewhere like this. For this particular vector, a perpendicular bisector I will draw somewhere. I will draw a perpendicular bisector somewhere like this. Somewhere here is a perpendicular bisector. So somewhere like this is a perpendicular bisector. So for this line vector, I have a perpendicular bisector like this, going something like this. For this particular line, I have a perpendicular bisector which is like this, and so on. And this particular line has a perpendicular bisector which will look something like this. So now what is the smallest area that is enclosed? Let us draw that part. So here is the smallest area which is enclosed in this. So that is the first Brillouin zone. So that is the first Brillouin zone. And of course, vector to any lattice point, and like I said, you have to draw this for all. So I could have drawn another vector like this, black. I should have drawn also a vector like this. Like I said, draw vectors to all the lattice points, and then you have to make perpendicular bisectors to them. So once you make the perpendicular bisector, you would have made the perpendicular bisector for this like this. You would have made a perpendicular bisector for this particular vector somewhere like this. But you see that these would have been still outside, they would not have come in play in defining the smallest volume. So essentially, if you draw this with few neighboring, so you can, because I could see in this that all you need is neighboring vectors only in the neighboring lattice, therefore I drew only those. But in principle, you should draw all of them and draw perpendicular bisector for all of them, and then define the Brillouin zone. So here it is, this is the Brillouin zone. All right. So now in this Brillouin zone, to keep my picture a little bit cleaner, what I am going to do is first erase what I have just drawn again. Little bit later, I am going to erase these portions, because it is going to just otherwise make my stuff dirty. Now I am going to show you something else. Now I am going to show you. So this is how the Brillouin zone is made. Once you understand what this Brillouin zone is, then I am about to tell you that on these Brillouin zone boundaries, actually anywhere on the bisector planes, even here, even in this region here, even at this point here or this point here, there is a condition which is satisfied. So I am going to write this Bragg's diffraction condition now. As I am going to write this as small k dot with capital K, small k. What is small k? Remember, small k is the wave vector which appeared in e to power j. That was the kind of solution we had, right? Plane wave. So that is the wave vector dot reciprocal lattice vector. What is the reciprocal lattice vector? Remember, reciprocal k is equal to, in this case, m1 b1 plus m2 b2, where m1 and m2 are integers. So that means you can generate by having this b1 b2, this b1 b2, some m multiples of m1 and m2, you will generate any lattice point. So from any origin here, all these vectors, black lines I have shown you, are essentially capital K vectors, and they are using some value of integer value of m1 and m2 to reach to other lattice points. So these are that is the K vector is equal to half K squared. Half K squared is what is equal to, and I am saying this is the Bragg diffraction condition, which is equivalent to saying 2d sin theta equal to n lambda. I will show you that in a minute, but this is equivalent. I will show you that they are equivalent. Now, let us see in vector form what happens. So, you look at the vector form. So, let us now take, I will use now red or some other color here, and let us take any vector now this. Let us say this is k. So, this is small k, some vector k, any vector in reciprocal space is small k, and then now what is this vector? This vector is capital K by 2 vector. Remember, in this case, this capital K which I have just written, I have written it as equal to B1, where that means I have chosen M1 equal to 1 and I have chosen M2 equal to 0. That is what I have chosen here. So, therefore, this is showing up as, so K by 2, I am writing as K by 2, black line which is whole vector is capital K, and this is only half of it because it is perpendicular bisector. So, therefore, this is K by 2. Now look at what happens anywhere on this boundary. Small, what is the dot product between K and capital K? Now, you can see whether this condition is satisfied or not satisfied on this boundary. If K lies on this boundary, so it is lying right here. If I take the dot product between these and these, now K small k dot capital K, what is that will be equal to? That will be equal to that K will be equal to essentially, now you can clearly see K square by 2. That is what this will be equal to. As you can see, if I take the resolve small k onto this, so K of K dotted with a unit vector in this direction will be equal to K by 2. If I take the component of small k in direction of K, that will be clearly K by 2, and of course, then I multiply by K itself, and that by dot like this, that will be, or rather then I should write it as just simply as this quantity multiply by this quantity, it will be K square by 2. That is what this quantity will be. So, clearly the Bragg's diffraction condition therefore is satisfied on this particular plane. So, on Brillouin zone boundaries, they are special, Bragg's conditions are specified. Now, only thing let me try to show you is that how K dot K is indeed equal to half K square. We could precisely define it, is equivalent to 2d sin theta equal to n lambda. This is a more common form in which you would have seen the Bragg's diffraction condition. It is pretty straightforward. Small k of course is the wave vector. It's simple, small k is simply 2 pi by lambda. That is what this small k is, and recall also that k of course is, k vector is equal to m1 b1 plus m2 b2 plus m3 b3 in general. I am writing in general form, and d spacing between the planes. So, if I have these planes, atomic positions, and this is a d spacing between them, then the d spacing between them of course is equal to 2 pi by k magnitude. That is the spacing between these. So, now if I write this part, if I write k dot k, so then I will write this as, and then what is the, and then we say theta is angle between wave direction and the planes, that means normal to the plane, and k vector of course is normal to these planes. This k vector is normal to the planes. So, they form the planes. Therefore, I am going to write this as small k as 2 pi by lambda, and I am going to write this as so 2 pi by lambda into dot product with k. I am going to cancel 1 k magnitude with a square here. So, in terms of magnitude I will cancel it out. So, if you resolve k in direction of k only, so if you take in the unit vector capital K, then that angle, this is the angle, then it should become sin theta. That should become sin theta. K dot k should yield, or k dot unit vector in direction of k would be k sin theta. That is what this quantity will be. So, that is actually that is what exactly, that is how I should have written here also. So, what I have done is k in with the unit vector in direction of capital K, and then a magnitude of k there, which would have cancelled on the right hand side. That would have been an easier way of doing things, which I am doing here. So, if that is the case, then if this is k sin theta, then I have another magnitude of k I should write here, and then I should write here half. I am substituting into this equation. I mean, in this equation I am substituting all this stuff. So, then half k magnitude square, and then I should have written 2 pi by lambda sin theta equal to then half k magnitude, which I would have written. What is the k magnitude? That comes from this equation right here. So, that I can write as 2 pi by d spacing. What does that mean? That leads to d sin theta equal to lambda, which of course we write as d sin theta equal to n lambda, n being the order of reflection. So, that you can see. So, I have shown you this, that indeed on these Brillouin zone boundaries this Bragg's diffraction condition is satisfied, and I showed you geometrically. So, should I, before I just quickly end, I am unhappy with this kind of thing calculation I did. So, k dot k in this case is equal to, you can see, k capital K by 2. So, that is what I have substituted in here to get this equation, which hopefully you can now see more carefully, you can see a little bit better. Okay. With this, let us close this chapter on today's lecture on this Brillouin zones, and now I am going to start moving into electrons in a crystal in the next lecture. Thank you.